Okay, so you are now experts on metabolic pathways. So now we go into our discussion on the actual pathways, right? So you know the overall idea. So series of enzyme catalyzed reactions. We know that the final product of one reaction serves as a starting reactant for the next reaction, right? That we know that pathways can be catabolic, being destructive, or they can be anabolic. So when we sort of jump ahead, chapter 10, so we're gonna, I don't know why the sequence is weird, but chapter 10 is the actual formation of glucose. In that process we call photosynthesis. So the sun is the energy, that kinetic energy of these solar photons are captured. We then convert that energy into a actual molecule, tangible molecule that we call glucose. Right? And that's kind of where we begin in chapter 9. So chapter 9 starts with glucose. It's like somebody baked the cake. They baked the pie, right? And then we go and now we're going to consume the pie. We're going to cut it apart. So I don't know if you've seen these big fancy cake decorators, Cake Boss or whatever. They put a lot of effort to make these real beautiful cakes. They made a lot of time and energy, baking, detail, artistic talent to make this beautiful cake. And then what's going to happen? It's just going to get cut and consumed, right? So that's kind of the role of photosynthesis. It takes a lot of work, a lot of effort to make glucose. And then glucose is then going to be broken apart in this first pathway that we call glycolysis. So we're going to look at 3 overall catabolic reactions, right? They're going to be glycolysis, which is what we're going to talk about in this discussion. And then we're going to look at cellular respiration and fermentation. So we'll get to those in a bit, right? Let's start first with glycolysis, the first of our catabolic pathways. There's 3. There's one anabolic pathway that is photosynthesis. So we're going to look at this yellow rectangle here, right? Glycolysis. So glycolysis will take place not in the mitochondria, but outside in the cytoplasm. So glycolysis is going to be the way that that prokaryotic cells can generate ATP, and also eukaryotic cells can generate ATP without necessarily going into the mitochondria. We are going to eventually get into the mitochondria, but that's in a later pathway, right? So we're going to look at the 3 metabolic pathways, 3 catabolic pathways that are used for the catabolism of glucose for energy: glycolysis, fermentation, and cellular respiration. Cellular respiration is made up of 3 sub-pathways, so it's a lot of stuff there, right? But right now we are in glycolysis. Right now we are out here in the cytoplasm. So what is glycolysis? Glycolysis is a catabolic pathway. It's going to be comprised of 10 chemical reactions, right? 10 steps, 10 chemical reactions that generate 2 molecules of ATP, 2 NADH molecules, and 2 pyruvates. And we haven't really covered these. We haven't discussed NADH. We haven't discovered pyruvate yet. All we've focused on is ATP, adenosine triphosphate, right? So glycolysis is not necessarily one thing. It's a pathway, but it's made up of 10 individual reactions where we start with glucose in the cytoplasm of all cells, and we're going to generate 2 ATPs, 2 NADH, and 2 pyruvates from one glucose molecule. Yeah. So that's the what. Again, the what is pretty easy to memorize. The how gets a little bit more intricate here. So let me first introduce you to nicotine amide dinucleotide, NADH. Right? NADH is 2 of the products that we're going to generate in this pathway. It's a busy molecule, right? But what I want you to focus on is this sort of reversible reaction here. We can undergo reduction and oxidation. And some of you still remember this. That's good. Some of you may have forgotten. You got to remember that again. Reduction is the gaining of electrons. Oxidation is the loss of an electron. So it's a reversible process that nicotinamide can go through. It can exist in a oxidized form, or it can exist in a reduced form. So NADH, nicotinamide dinucleotide, right? I like to think of it as an electron Uber, a taxi. It's a transporter of electrons. So NAD, if it is like an empty Uber car, right? The car with no passenger. So it has capacity, has space for electrons. That's the NAD. Once that the passengers walk into the Uber becomes full, right? It can't take any more passengers. So it gets a passenger, it travels, it drops off the passenger. So same thing with electrons. So NAD can accept an electron, and when it does, it brings the electron and it brings in also hydrogen ions, right? So this is the reduced sort of idea, NAD or NADH. And then when it gives up the electron, it gives up back the hydrogens, and we have that cation. Remember, oxidation leads to cationic charges. So NAD plus gave up the electron, NADH picked up the electron and the hydrogen luggage with it. Yeah, I hope that's making sense, right? So NAD is an electron carrier in the cellular redox reactions, reduction and oxidation reactions, right? So it exists in the oxidized form, NAD plus, no electron, and the reduced form, NADH, yes electron and hydrogen luggage there. So it's the two things. It can shift between the NAD plus to the left and NADH to the right. NAD plus, NADH, NAD plus, NADH. And it just kind of goes back and forth, back and forth, back and forth, picking up electrons, transporting electrons. So NAD plus has a very strong affinity for electrons. I like to think of it as maybe your kitchen table, right? Let's say you're eating at home. If you live here in El Paso, I bet there's a very high statistical chance that you have a little overweight dog, a little overweight chihuahua there in the kitchen, yeah? And if any food falls there, that little dog's gonna come pick it up. If you have a little dog, the 5-second rule does not apply. I don't know if you're familiar with the 5-second rule. Right? 5-second rule, you drop a piece of food, 1, 1,000, 2, 1,000, 3, 1,000. Well, it's still good. You know, clean it off a little bit. If you have a dog, the 5-second rule doesn't apply because that food's going to hit the floor. It's going to get swooped up right away. So I have a picture of a dog here that would act as a hungry NAD plus, looking for any little morsel of food, any little electrons that come by that will get picked up, and it will undergo reduction very, very efficiently. So that's sort of the idea of what NADH sort of does. And again, we're going to end up with 2 loaded electron transporters after this 10-step reaction. So that's the NADH. So I hope you're ready. You're ready for the roller coaster that is glycolysis. Yeah, a lot of chemistry here. So I'm going to walk you all the way through it kind of fast, and then we're going to come back and slow down and look at it a little bit more detail, and I'll try to explain some stuff a little better, right? But we begin this mess in the cytoplasm of all cells, both prokaryotic and eukaryotic, with glucose. Once glucose enters into the cell, that's basically that molecule acts as a substrate for the first enzyme that we call hexokinase. And how do we know this is an enzyme? ASE. Remember those last 3 letters? So glucose interacts with hexokinase and we lose an ATP. So we invest in ATP at this point, right? So glucose gains a phosphate. So we call that now glucose 6-phosphate. It's got a phosphate on the 6th carbon. Glucose 6-phosphate, then the final product of the first reaction, serves as the starting reactant for the second reaction. So it becomes a substrate now for phosphoglucoisomerase, right, to produce fructose 6-phosphate. So if we look at that molecule, we shifted the molecule a little bit. we broke that hexagonal shape and now went to a pentagonal form. So we can't call it glucose anymore, we call it fructose. Here we invest another ATP, and phosphofructokinase interacts as the enzyme to generate fructose 1,6-bisphosphate. So we have a phosphate on one side, a phosphate on the other. At this point, aldolase gives us the name, right? Glycolysis means the breaking of sugar, right? So that's the breaking of a carbohydrate, of a sugar. And that's what happens. So think of it like in a karate, whoosh, we break that 6-carbon molecule, carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. It gets broken. That molecule breaks into 2 3-carbon molecules here. So carbon 1, 2, 3, carbon 1, 2, 3. And that's where we get the name glycolysis, right? So we broke that bond, electrons became available, and electrons then get picked up by NAD plus to form NADH. We have a reloading of inorganic phosphates. So we're back to 2 phosphates here, and there's another, right? So if you see here, there's 2 of these molecules. We do the same event twice. We have another enzyme. We start to then peel off those phosphates, give them back to ADP to produce ATP. And that happens reshifting. I ran out of space here in the slide. But we have enzymes, and eventually we peel off that last phosphate, give it back to ADP to produce ATP. And what are we left with at the end? Right? We're left with a 3-carbon molecule that we call pyruvate. We're left with 2 ATPs here and 2 ATPs here. And we're left with 2 NADHs. So in total, right, we form 2 NADH, 2 pyruvate molecules. The half, think of a 6-carbon molecule. You have a Kit Kat bar, you break it in half. So you have 2 equal-sized pieces. So we have 2 halves of the original glucose. And we did form a total of 4 ATPs, but we had invested 1 and 2. So yes, we do form a total of 4, but we have to invest 2 initially, so we only have a net total of 2 ATP. So again, to kind of show it in a slightly different way, think of the little black marbles here. So 1, 2, 3, 4, 5, 6. There's our 6-carbon glucose molecule. We invest 2 ATPs. We then break that 6-carbon molecule into 3-carbon and 3-carbon. We load more phosphates, and then we peel off those phosphates and give them back to ATP. To form ATP, we get our electrons to NADH. Again, for a grand total of 1 pyruvate, 2 pyruvates, 2 ATPs, 4 ATPs, 1 NADH, 2 NADH. So 2 NADH, 4 ATP, and 2 pyruvates. But again, we invested 2 ATPs, so we only have a net profit of 2 ATPs here. Now, why did I show this little picture here, right? I don't know if you've ever seen something like this. So maybe somebody stole a bike, right? They stole a bike. Oh, that's recognizable. Let's change it up, right? Let's spray paint it, change the tires. This original bike looks different because it was changed. It was sort of hidden, right? This little puppy looks very, very furry. It's the same puppy, but it's been shaved, right? So the before and after the manipulation there. If I come back over here, this is what the cell is trying to do, right? The cell works hard to acquire glucose. So once glucose diffuses in, right? Once insulin has done its job, once glucose is diffused into the cell tries to trap it, right? It spins ATP to make it look different. Oh, make it look different. We don't want glucose to be recognized. We don't want it to be able to diffuse back out through that same channel. We want to trap it. Is that enough? I'm not sure. Let's change it some more, right? Let's invest another ATP to be sure that it's not going to escape back out, right? And once it's at this point, it's no longer recognizable. It doesn't look like the original glucose. This is the before. This is the after. Now the cell can relax and start to break it apart, tear it apart, strip off as much energy as we can from that glucose. And again, glycolysis is only the first pathway in which that begins. It's not efficient. We only get, again, 2 pyruvates, 2 net ATPs, and 2 NADHs. So I'm going to leave you with these slides here. I'm not going to lecture on these. This is for a biochemistry class that you'll take later. Right now, I just want you to get the idea of what do we mean by a metabolic pathway, what are the starting reactants, what are the final products of these intermediate pathways. But if your brain, my brain works like this, where I need more information. I need more information to make sense of all the details, then I can simplify it later. So I'm going to give you these for your reference, right? It's the step 1. What happens? There's the enzyme in red. Kind of gives you the name of the molecules, enzyme in red. So step 3, step 4, step 5, step 6, 7, 8, 9, 10, right? So again, after those 10 reactions, starting with glucose, invest in 2 ATPs, all the reactions and breaking and shifting, everything that happens, again, we're left with 2 pyruvate molecules, 2 ATPs, and 2 NADHs. And that's that first catabolic pathway that we call glycolysis. I'll upload a video at the end that summarizes everything, right? So the whole process. All right, so let me stop this one here and we'll continue onwards.